Hey everybody. Today we're talking about statistical independence, or just independence. We're in a situation where we have two events, A and B, and the probability of them both happening, that is to say the probability of A intersect B, is just equal to the product of the two individual probabilities. Probability of A times the probability of B. When the two probabilities are non-zero, this definition is equivalent to another one that's sometimes a little bit more intuitive. The probability of B given A is equal to the probability of B, and the probability of A given B is equal to the probability of A. If the individual probabilities are non-zero, either one of those two conditions there is sufficient. Each one of them says that the conditional probability is equal to the unconditioned probability. In other words, taking the first case there on the left, the occurrence of event A doesn't give you any new information about whether or not B might occur. Here's an example. A manager studies the accuracy of orders in their restaurant, and the results are in this table. So we have meals for breakfast, lunch, and dinner, and we have whether or not the order that was actually made was actually delivered to the person that ordered it. An order from this sample is chosen at random. Are the events the order was accurate, call that event A, and the order was at dinner time, call that event B, independent or not. I recommend pausing the video, giving this a try on your own before seeing my solution. We're going to need to find the individual probabilities as well as the probability that both of these things both occur. Starting with whether the order was accurate or not, that is event A, we see that there are 842 yeses in this set out of 960 total. So the probability that A occurs is 842 divided by 960, about 0.877. Similarly, the probability that the the order selected was at dinner time is 280 divided by 960 because there are 280 dinner time orders at this restaurant. That's about 0.292. Finally, the probability that both A and B occur, the probability that the order we selected is accurate and at dinner time, is 249 over 960, about 0.259. Plugging into the formula that defines statistical independence, we see that the probability of A times the probability of B is about 0.256, and that's not the same as the probability of A and B, which is 0.259. These events are not independent. We might say that they are dependent on one another. Notice that knowing whether one event occurs doesn't tell you with any sort of certainty whether or not the other event occurs. That's not the definition of statistical dependence. Rather, we're asking whether the occurrence of one event changes the probability of the other event. Next example. Suppose the probability of A is 0.7, the probability of B is 0.6, and the probability of A union B, that is to say the probability of A or B, is 0.88. Are A and B independent? So we're going to apply the addition rule to the probability of A union B. That says that that probability is equal to probability of A plus the probability of B minus the probability of A intersection B. Plugging in the things we know and then doing a little bit of arithmetic, we find that the probability of A intersect B, A and B, is 0.42. Now we can check the condition for statistical independence. The probability of A and B is 0.42. The probability of A times the probability of B is 0.7 times 0.6, or 0.42. Those probabilities are the same, so the two events are independent of one another. One important fact is that if the two events A and B are independent, then so are their complements in any sort of combination that you might choose. A and B complement, A complement and B, A complement and B complement. All of those things are independent. I'll just prove the first one. It's short. We're just going to apply the multiplication rule for conditional probability to the probability of A intersect B prime. And then once we get the probability of B prime given A, we can use the rule of complements on that. That probability is equal to 1 minus the probability of B given A. The probability of B given A is just equal to the probability of B, since A and B are independent, and then 1 minus the probability of B is the probability of B prime. All the other parts of this fact that I showed a second ago are proved in exactly the same way. Three events A, B, and C are said to be pairwise independent if any two of them are independent from one another. For instance, we have to have the probability of A intersect B is the probability of A times the probability of B. Interestingly, on its own, that doesn't guarantee that the probability of A and B and C is equal to the product of A, B, and the product of the probabilities of A, B, and C. Here's an example illustrating that. Flip two fair coins and consider these events. A is that the first flip is ahead, B is that the second flip is ahead, and C is that both flips are the same. We're going to show that these events are pairwise independent, but that the probability of A times the probability of B times the probability of C is not the same as the probability of A and B and C. Each of the individual probabilities here are 1/2. The probability that either of the flips is ahead is 1 in 2, 50-50, and the probability that both flips are the same is also 50-50. Regardless of what the first flip is, you have a 50% chance that the second flip will match it. The probability of any two of them happening is 1 in 4, as you can confirm directly. The event A and B and C only occurs when both flips are heads, so its probability is 1 in 4. So the probability of A and B and C is 1/4, while the probability of A times the probability of B times the probability of C is 1/8. The situation here is one where neither A nor B gives information about C, but if you take them together, they do. In this particular case, if A and B both occur, then C is guaranteed. If both the first two flips were heads, then obviously both flips were the same. Three events, A, B, and C, are said to be mutually independent if they're pairwise independent and the probability of A, B, and C is equal to the probability of A times the probability of B times the probability of C. And you can take this definition and extend it to a larger collection of events if you need to.